concentrations that always gave you equilibrium concentration. Today we're going to do some for equilibrium concentrations find the K value, or K value and a few of the concentrations find the last concentration, so on. Now we're going to give you some things that don't give you equilibrium concentrations for everything. And we're going to work through this example. Copy this example, not the circles. Copy the text. Call this ice charts. Call it all of this. Okay? This other than the circles. ICE, initial change equilibrium, that's you're going to see. I'll give you guys a few moments on pause and take a white time. Okay. ICE charts. ICE, by the way, stands for ICE. The initial change in equilibrium. We've kind of been doing this when we started the unit and we were doing charts, like at decimal 1 second, decimal 2 seconds, decimal 3. And now something goes down, the other side goes up, and then the balanced numbers from the balanced equation and so on. That's kind of what we're doing here, but we're not doing a full-blown chart for every second in between. So let's take a look at this. So if I do this, I say initially, concentration of nitrogen monoxide is 2. Nitrogen is 12. Oxygen is 10. Okay, I'm going to be filling that in. I gave you a balanced equation, and I've set it up here so that this is like the headings for a chart. So this column right here will be for nitrogen monoxide. Okay, so these are the headings of the columns, and then this, I don't put the grid line. And this is the line for initial change in equilibrium. So that's really what we're doing, but I don't draw it. Okay? Now you understand. Now, initially, NO's concentration is 2. Use units in these because I'm a real jerk about it. I'll take marks off. Nitrogen is 12. Oxygen is 10. Okay, that's my initial value. And at equilibrium, 7. Oxygen. I'm going to skip down and put this in line with the equilibrium line, so I'm going to need space. It's oxygen. Now, in green, I've given all the given information. The rest we've got to figure out. Now, how does this work? Question. No, it is actually, that is the measured concentration. Now, the balance numbers don't tell you the good question. So what he's asking us is, do I double it, basically, because it's a balance number too, right? Yes, remember when we were doing our charts, the decimal 1, decimal 2, second, decimal 3? What did the balance numbers tell you? It's not the amounts, but the changes, right? The change on this side will be in a 2-to-1 ratio for that side. Because these, we don't have a number, so we're assuming it's a 1, right? The property balance. Okay. So that's the only thing that the balance equation tells you. Now, because it's your first time, I'm going to just go through this with a picture as well. And I use whole numbers as well, 2.0, just so we can demonstrate this. Now, it's 2 moles per liter, 12 moles per liter, 10 moles per liter. But we're going to pretend that we're going to represent 1 full mole with 1 molecule at a time. So my drawing, I'm not going to write 2 moles worth, like 602 times 10, I'm not going to write that many molecules there. It would be more than that. I couldn't do it. So if I have 2 NOs, you'll see, I'm representing that. Now, I'm using yellow for oxygen and atoms and blue for nitrogen. I think that's good, isn't it? So I've got 1, 2 of those. That's what I'm representing there. And I should have 12 N2s. So I have 12 blue ones. 1, 2, 3, 4, 5. Oh, there's the. Try this again. Count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I do it. And I should have 10 oxygen, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, we'll pretend there's a container. I don't have a perimeter. These are gases, so they're floating around. Why do reactions happen in grade 10? You guys talked about this. Two things I need to have. Gas molecules are they're floating around, and there has to be collisions. And some of the collisions lead to nothing. Some of the collisions, they just bounce off. Sometimes the collisions are strong enough that, and it doesn't matter if this collides with another one of these, this collides opposite, this collides with that one, this collides with that one. They're just collisions, and they're random, right? Because they're gas particles, and they're going in all directions. But if the collision has enough energy, what might happen? Can you talk about this later? What reactions happen? The reaction rate. Little bit. Can't do anything without the structure experiment. Karate did. Oh yeah, you guys were twins too, wasn't it? Well, this is a good thing I'm going over this. Anyways, so when these collisions happen, sometimes they have enough energy that they break apart the bonds inside the molecule. We call that intra. But anyways, so a couple of things bounce together. And these guys come apart. And these guys come apart. They might then, now they won't stay apart for long. They might come back together on themselves. But if they randomly bump into another, so these guys had a collision, these guys had a collision, hey, this might happen. Then you got some free guys out in here. But this might happen, and so on, right? Now, I just reacted one oxygen with one nitrogen to form NO. I'm taking the reaction this direction. That's where it's going. But it's going back and forth at the same time, too. Some of those are coming apart, too. The NOs are coming apart. But then, on average, just as many, okay, you guys know how this. But this hasn't reached equilibrium yet, so it's got to shift. You notice from here to here, 10 to 7, this goes down. So I've already reduced one of this. But if it goes this direction, every oxygen that reacts, you have to have one nitrogen that reacts. Right? So I've done one of those, right? And lose track on this. So some more collisions happen. Everything's going forward and reverse at the same time. Stop again. What am I at for oxygen now? Okay, I've got to do another reaction, right? And I'll just randomly take some. All right. Now, have I gone down 7 here? I just count. 702. That's what we're told. 1, 2, 3, 4, 5, 6, 7. That happens. You're never going to draw this up. I want you to realize the net result is 7. So you're not going to draw a molecule. You have to have a way to do this. Drawing. So what's the arithmetic here? What's the change? How do you go from 10 to 7 arithmetic? Minus 3. I'm going to call it 3.0. And that gives me 7. Now that makes sense, right? I took apart 3. You saw me, right? Yeah. You know it's a 1-to-1 ratio. And these are both on, I'm drawing a thick line that will disappear. They're both on the product side. So So if the product side's going down for oxygen, it's also going down for nitrogen. And it's in a 1-to-1 ratio. This is exactly what I'm talking about here. So if it goes down by 3, the nitrogen goes down by 3. And the arithmetic works 12 minus 3. Let's double check that the arithmetic works. That means I should now have 9 blue pairs, the nitrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9. I do. Okay, so the arithmetic works, right? If the right-hand side going down, what's the reaction to the left-hand side? Ah, and if the balance numbers, I'm going to use oxygen as a comparison. 1. If this goes down by 1, this goes up by 2, right? Well, I think you can do the arithmetic. If this goes down by 3, this goes up by twice as much, right? Yeah. Now, you're going to have decimals and stuff like this. So you would multiply by 2 if you can't go, if it was like 3.372 or something like that. You'd use your calculator. But right now, I've chosen the first one. So it's going to be increased because it's the opposite side and twice as much. So the balance ratio. 2 plus 6 is 8. We've done that. 8. Verify that we saw 1, 2, 3, 4, 5, 6, 7, 8. I do. It works. So sometimes just the first time, I think it helps people see a visual representation that helps it. Okay? That's what I showed. Now we've done one real slowly. I've only just begun. I didn't actually solve the problem. I need to find the value of K. But to do K expression, we need products over reactants from the balance equation. And then to find the K value, that's the numbers. You have to use equilibrium concentrations. You can't use initial ones or change numbers. Essentially, this is like the charts we did in the first part of the chapter. Except that I'm not going like 1 second, 2 seconds, 3 seconds. I'm going, this is where to start it at, times 0. This is when equilibrium was established. I'm basically skipping all the middle stuff. Does that make sense? Because you had charts with 5 or 6 lines. This is just a repeat of this. Don't copy this up. You've done the rest. What we do need to do is, you just keep that this. We got to figure out the problem. K equals. Now I made up numbers. They aren't actually realistic for this chemical system. It's just for the calculation ease. You know how to do the expressions. Yeah. You do a problem like this. You're going to do an ice chart, of course. Figure out your equilibrium. You're going to have units in them. Then you're going to get a mark also for the K expression and then the K value. Put in my numbers and then slide up again. 9 and 7. Over what? 8. Well, I don't need the units in here. I told you that before. You don't need units. Don't put units in the K calculation. Right. 97. That's messy there. And this is a calculator issue. This one's not tricky. I'm going to just tell you. You put 9 times 7. 5 by 8 squared. It's really divided by 64. 0.9. No unit necessary. How are we doing? I've built this up in baby steps. Expressions, then we did some calculations. Now we're full blown bigger. I'm gonna flip her. Once again, I've got a diagram. This is starting. Write this down in my ICE. I'm not going to use the full words, initial change in equilibrium. I'm just going to use ICE. You need to know what it stands for. I'm going to pause the video and start that down. Use your imagination. Find the KQ for the dissociation. Now that's a word. Kind of loosely means dissolve. PBR2. Then 2 goals. If its solubility at equilibrium is 0.05 moles per liter, that was the first. First, you'd write the balance reaction. I have it written for you. PBR2 solid. Double arrow, so back and forth. In water, you don't actually add H2O because it's not the chemical. It's not a chemical. It's not incorporated into the PBR. Right. But solid turns into these aqueous that dissolve in water. Ions. And that's important because solids don't appear in decay expression. So on your ion chart or your ice chart, you're going to do this. Put a line in here. Because if it's not in the K expression, you're not going to use it in the ice chart. We're only using gases or aqueous. And I'll never have a problem for you where you have gas and aqueous. I make sure. It can happen, but we won't. Now, I don't have anything here for initial. Previous problem I did. Whenever you have a solid that's dumped into, let's just do some imagination. That would be here. Yeah, I'm not measuring the solid. Okay. So we're pretending to have a liter of water here that's carefully measured. How much? Yes. You're missing some exciting stuff. And PBR2. Water. Anyways, I'm not measuring out anything here. How much initially lead ions and bromide ions, how much is in this beaker right now? You saw it before, even if it was from the strip. How much is in here for the lead ions? Have I added it? No. So the very second that I'm adding this, right now, there was 0 ions, right? That's just as I started. It takes a second for the equilibrium to go through. Ooh. Floodgates. Okay. So we're going to write down 0. And that's an assumption if you have a solid that's dissociated. Now, dissociation is the word that we use instead of dissolve when you have something like sodium chloride, like table salts, or any ionic compound that breaks up into its ions. The better word is dissociate. Ionic compounds dissociate water. Things like sugar, which are molecules, don't break up into water. That's true dissolving. Okay. That solves that problem. This is like the other problem. We have initial concentrations. At equilibrium, its solubility at 0.5. You got to use a little bit of logic here. That means, I'm going to just talk about 5, but we know when I say 5, I mean 0. 5, 100. If 5 of these break up, how many of these fall? It's a 1-to-1 ratio, right? So if that goes down on the left, it goes up on the right. And it can only go up because it's starting at 0. So if one of these, one of those fall, right? So if 5 of those break up, 5 form, right? Okay. I'm going to put this. Likewise, PbBr2 to the bromide ion, it's a 1-to-2 ratio. So 2, twice as much, right? 5 times 2 is 10, so 0.2. I don't need to put it behind 0 now, because it's 0 grams per liter, it's 0 moles per liter, it's 0 whatever. You can put the 0 in. That's the only time you don't have to use it. I'll put it there. So, okay, the arithmetic is pretty easy here. It's plus 10, plus 5. That part of it, these are his charts on that. Now, I'm just going to mention something. I just told you I didn't measure out how much I added to that bucket of water. But remember, this is an equilibrium. It didn't say how many moles I added to the water. What do you notice at the bottom of this? See? It's all white sitting at the bottom. I added way too much on purpose. It'll never dissolve. Even if I stir it around, and I'm not worried about these chemicals. I just stir it around. It'll get cloudy and misty. And you know what? In 5 minutes, it'll all settle back to the bottom too, right? Here's the idea. I'm representing them as molecules, even though they aren't. An ionic solid is not little discrete units of PbBr2. It's not, but it's easier to think about this as far as it. However, all this stuff sitting at the bottom, any second, what's happening? It's equilibrium. So if one breaks up, it goes into solution. Let's just do that. One of these guys breaks up, goes into solution. What happens at the same time? Floating around. These guys are floating around, and it's gonna, something else is gonna bump into one of these, right? And they're gonna float down when they come together, ionic return, right? The equal rates forward and reverse at any given time. I forget it. I just count ahead of time. About 5 and 10. Probably. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 10. They're in that ratio because they started out at 0. Every time one PbBr2 breaks up, some other things come together and read, right? On average. These are huge numbers, so it's going to happen, and that average will stay the same. So you can see already, I swirled that up. Got the white stuff sitting at the bottom already. 2 minutes later. So that's what we're observing. But that's why I don't even need to know how much. As long as you exceed the amount that it can dissolve. And you guys know this. You ever make iced tea? You want it to taste stronger? Yeah. Because I know you like iced tea. That's what I thought of it. Where's your iced tea today? Well, you're drinking something different. Anyways. Wow. I don't want to die like you said it was going to be. Yeah, well, there's sugar in that too. Anyways, you're young and you've got probably 60 years of drinking iced tea before it affects you. But anyways, diabetes. Back to this though. Okay, you know what happens. Good host iced tea or no name or whatever. You want it to taste stronger, so you add another spoonful. What happens? You can add all you want. It just, after a point, it just sits at the bottom, right? Chocolate milk, same thing. It just sits at the bottom after you want a chocolatier, no luck, right? Okay. There's only so much, and that's that equilibrium. Okay. And you can re-stir it, and I remember all you're doing is suspending the, basically iced tea mix is just sugar particles. That's a bit of flavor on it. You stir them up, so then you do swallow them. Because that last sip of the iced tea that you made, you get a lot of sugar rush. Okay, so that's what we're talking about here. Let me finish this up. Now, that's the process. Now the calculations back to this. Find the KEQ. That's what it really needs to do. This is the same problem as the other one, right? KEQ expression. I have to put 2 plus because it's an I. With PB without the charge, it would be a solid and it wouldn't be BR negative, so it's the anion. You guys are familiar with the word anion for negative? Yes or no? Yeah, cation. There's no denominator because it's a solid. So that just means my calculation. Now, once again, I used easy numbers so that this isn't actually realistic. I didn't say what temperature is. As you know, temperature affects the dissolving. Okay, and then it's a matter of just plugging it into your calculator. 5 times 0.05.